All right, 2020 E&M practice problem that was invented for the spring review period. And they give us a sphere of charge, and then they give us an electric potential graph that is shown as a function of position. And we scroll down, let's see here. There we go. This first response space doesn't need to be there. I have no idea why that's there. Part A. What's the farthest position from the center that you can put your ball and let it roll away and exit the sphere? So if it's going to exit the sphere, that means it has to get past 10 meters. If it's going to get past 10 meters, then it has to start no farther away than x equal to 2 meters. Remember, the potential graphs are an indication of, you could do mountain and valley as we discussed in class. So if I put a ball here at 2 and I let it go, it's going to roll down into the bottom of the valley, roll back up to the same height. So if it's at a smidge less than x equal to 2, then it will get over this hill on the other side with a tiny amount of velocity. So for part A, r needs to be, the absolute limit is r equal to 2 meters, and this has to do with conservation of energy. And that's what they want to see for part A, that you select the correct position and that you indicate we have a conservation of energy situation here where you need to give it enough energy to be able to get over the hill on the other side of the sphere. All right, part B. Now we're going to release the ball at that position, and they want to describe the magnitude and the direction of the acceleration. And they only care about the acceleration between 5 and 10. So let's think about what's going on with the acceleration here. First thing is acceleration points left. Or you could say toward center of the sphere. Second thing, at the bottom here, the acceleration is 0. Then as the slope increases, the acceleration increases, and then the slope decreases. So acceleration goes from 0, increase, and then it decreases back to 0, back to 0 at r equal to 10 because the graph is horizontal there again. Third feature about acceleration, and remember they only care about acceleration, they don't care about velocity, and they told us about position, so we don't even really need to comment on that one. Third thing about acceleration is that acceleration points toward that's supposed to be an L, toward lower potential. So as the ball is here, the acceleration points left, and the left goes along with the lower potential. And the fourth thing that you need to indicate or could indicate is that acceleration is proportional to the slope of the graph. Remember that the electric field is the negative derivative of potential with respect to position, and the electric field is force divided by charge, and force is mass times acceleration. So stringing these guys together, acceleration is equal to charge over mass, negative, and then electric potential with respect to position. So it points towards lower potential. It depends on the slope. Where the slope is 0, the acceleration is 0. where the slope is increasing, the acceleration is increasing. And because our potential increases to the right, that means acceleration being the negative of that, that means acceleration points left. So this one equation hints at all four of these guys, but you need to spell it out because they're looking for a short answer response here. All right, part C. Turns out they didn't put a question here. That's really obnoxious. My guess is, based on looking at the answer key, is that they wanted some sort of description to say, how does this equation work? Like, what aspects of that equation are good? So one aspect of that equation working is that the electric field, E is negative slope of potential. And it works, fits at R equal to 5. And the second part of that goes along with it, like a specific point, is it fits it at R equal to 5. If you plug in 5 here and they told us that B is 5, 5 minus 5 is 0, so the electric field is 0, and if you take a look at the graph, the slope is 0 at R equal to 5. Another thing, along with the negative slope, is E is plus, points right, for R less than 5. So if R is less than 5, and remember B is 5, we're going to get a positive number here. And if you take a look here, if we put a ball anywhere R is less than 5, it's going to get pushed to the right, which fits along with the electric field should be pushing it to the right. And a corollary is negative, or left, for R is greater than 5. So as soon as R is bigger than 5, then we have B minus a bigger number. We get a negative answer. And our electric field, now for the ball being over here, the electric field points to the left. This is how it works. And I think that's what they meant to ask for part C. Provide some justification for why the student would choose this function to model the electric field. When we scroll down to part D, we're going to see the question for, okay, where does it fail? But I'm going to have to clear these things out before we get there. Okay, part D. State one feature that does not model the electric field. Okay, so remember that the electric field is supposed to be the negative slope of the electric potential. If we take a look at the graph, the electric potential should have a slope of 0 at R equal to 10. But if we look at the function that we were given, 4, 5 minus R, if we plug in 10 here, 10, then we get a negative 5, then we get E of 10 is equal to negative 20 volts per meter. That doesn't work because that's supposed to be a 0 here. Another thing is that the concavity of our electric potential function changes. So at about here, it goes from being concave down to concave up. And then somewhere over here, it goes back to being concave down. So concavity of V changes. If the concavity is changing, you should know from calculus class that that means the first derivative is going to be not linear. First derivative, learn how to spell, dude. First derivative is not linear. So this can't be a good function for that whole range of 10 meters because the concavity is changing, so that we can't have a linear function there. Those are two things that you can pick on. And part E. We did part E in class. I'm going to need space for this. All right, in class for electrostatics, we discussed situations where the charges were not linearly distributed. So we have Gauss's law, and you need to mention Gauss's law. And basically, if you do this on paper, and then you just narrate your steps. That's what they want down here for part E, is they want a narration of steps for how you would go about this. So the first thing that you would do is pull out Gauss's law. So use Gauss's law. And since we're talking about a sphere, you would need to make sure that you have the surface area of a sphere included there. Surface area of sphere. And in Gauss's law, we're relating charge to E field. Surface area of sphere times E on the one side. And on the other side, the Q enclosed is going to be the integral of density times volume of a sphere. All right, so you need to write Q enclosed is integral of rho times volume of sphere. And then you're going to substitute both of these guys in there. So we're going to have integral of rho r 4 pi r squared dr equals E 4 pi r squared. And then, well, this is an integral over the radius. So we need to take the derivative over the radius. So if we're going to do that, then we have rho r 4 pi r squared dr equals the derivative with respect to the radius of the right side of Gauss's law, and that guy disappears as part of taking the derivative. And then we're going to divide by the surface area of the sphere. So rho r equals 1 over 4 pi r squared after we took the derivative. All right, so here's 1, 1, 2, 3. 4 is, I should have written it down here. 4 is sub into Gauss's law. 5 is take derivative with respect to radius to find rho. Oh, I forgot epsilon naught, permittivity of free space. So when we're down here, we're dividing by that, and we're still dividing by that, and then over here we multiply by that. So we need to make sure that we include that. This is a somewhat awkward expression, and normally we don't do it this way. Normally we use our integral form, but that's how you could work backwards, I suppose, to get the volume charge density in the sphere.